All right, guys. So what we're going to be talking about today is continuity and the intermediate value theorem. We've talked a tiny little bit about continuity, but kind of one of the unfortunate things about Calculus 1 is a lot of times you end up talking about continuity before they define continuity. So I'm just going to go ahead and get in here and define it. Actually, I lied. I'm going to give you the idea of it, and then I'm going to define it. So, idea of continuity. Continuity. So, what's the idea of continuity? So, a function is continuous if you can draw the graph of the function without lifting your pen. So, what does that mean? Well, it means what I said. So let's look at a graph. Make that straight. Make that straight. So, a couple graphs here. All right. So if you have a function that looks like this, then you're able to trace this curve, just trace the curve all the way, and you never have to lift your pen. Now, if you have a different kind of graph, like maybe you have this kind of graph, then you can't. Because if you try to trace this graph, you trace it, you get up there, you have to lift your pen, come down to the bottom, and then start again. Okay? So the graph on the left here is continuous, and the graph on the right is not continuous. So continuous, not continuous. All right? Now, while we're at it, we may as well mention a couple of different types of discontinuities, I'll say, before we move on and give a definition here. So some types of discontinuities are a jump discontinuity, and let's see, what else are they going to talk about? Probably going to talk about, go back. Oh, that doesn't help. Stop. Jump discontinuity, and then there's going to be a removable discontinuity, and there are others, but I'm not thinking that they used them in the book, so I'm not going to describe them unless I see one in the next few minutes. So a jump discontinuity is actually what we just already saw. So if I take this graph here, cut it out. That did not work at all. Undo. Cut. Copy. Paste. All right. Got a couple of graphs here, so sorry about that. Took a while. So a jump discontinuity is when you have a function, okay, straight line, that's fine, and it jumps. So there you go. That is a jump discontinuity right there. All right. Now a removable discontinuity is a little bit different. So a removable discontinuity is a discontinuity where there's just a hole in the graph, and that's it. Okay, so they should make sense. The jump discontinuity should make sense for sure, right? Like you could see the jump. Yeah, so that's a jump discontinuity. Now, a removable discontinuity is called removable because there's a way to fix it. So these are called removable. These are called removable because you can remove the discontinuity. Right? So this function here is discontinuous, the one on the right, because if you try to trace the graph, I say you can trace it without lifting your pen. So you trace it to here, but you can't, you're not supposed to be covering over the circle. So, because the circle's empty. So you get to there, you have to lift your pen, and then on the other side of the empty circle, you start it again. So that's why it's a discontinuity in the first place. But why is it removable? It's removable because if you wanted to make this function continuous, all you would have to do is go to where that empty circle is and just fill in that dot. Right? You fill in that dot, now it's a continuous function. So we removed the discontinuity. So that's why they're called removable. Now we're not actually going to remove it right now. You just need to know that that's why. So if you look at the graphs, you should be able to tell the difference between a jump discontinuity and a removable discontinuity. Now let's actually define continuity. So continuity at a point. AB. Really? No, I don't need AB. I'm just going to say at A. At x equals A. Okay. Here's the definition. Very easy definition. A function is continuous at x equals A if the limit as x approaches A of f of x equals f of A. All right, that's the definition. And so if we look back at the functions that are not continuous here, let me pick one. Come on, copy, come down here, paste. So if we take a function that's not continuous right there, and I just add a little bit of drawing on here, so like if I say like this is, I don't know, 3, okay? Then the problem with this one, let me put some y values on here too actually. Call that 1, call that 2, call that 3, 4, okay. So I'm going to say that this is at, I'm going to say that that's at 3. Close enough. Okay, so if you look at this picture here, and let's say that this is a graph of y equals f of x, then I can do a limit from the left, a limit from the right, and I can do the function value. So let's do the function value first. What is f of 3? According to the picture, or what I just said, f of 3 is going to be referring to where that solid dot is, right? The y value there is 1, so f of 3 is 1. Okay, that's easy. Now, in terms of the limit, you need a limit from the left and a limit from the right. Those have to be equal for the limit to exist. If you do the limit of this function from the right, as x approaches 3 of f of x, then you would be tracing it on the right-hand side. So you're over here, you're tracing your curve this way, and where do you get? You get to that same point. So the limit from the left is going to be 1. Okay, but what about the limit from the right? If you do the limit from the right, that should be, sorry, that was the limit from the right. If you do the limit from the left, 3 from the negative side of f of x, then you're on the left-hand side. So you're over here somewhere. You're tracing the curve from left to right. So you trace the curve, and you end up at that top point. Okay, now that top point I said was 3. It looks a little bit bigger than 3. Here, maybe I'll do that. Okay, so it's bigger than 3. It doesn't matter what it is. So you get those pieces of information. Okay, but if you combine these two facts right here, then this tells you that the limit as x approaches 3 of f of x does not exist. Right? Remember when we first talked about limits on graphs that the limit from the left and the limit from the right had to give you the same number in order for the two-sided limit to exist. So since we get a 1 and we get a 3.2, and those are different, then the overall limit does not exist. Okay, so once you have all this stuff written down, then you can come back to your definition here, and your definition says a function is continuous if the limit equals the function value, right? That's what this says. That's what this says. Okay, well, does it? Well, f of a in this case is 1, right? So let me just summarize it here. So f of 3 equals 1, and the limit as x approaches 3 does not exist. The limit as x approaches 3 of f of x does not exist. So, I mean, look at that information there. You need them to be equal, but one is 1 and one doesn't exist. So we just conclude that this function is not continuous at 3. Therefore, not continuous at 3. Right? And so that's the idea. So that's why it's not continuous at a jump, because the left and the right-hand limits don't exist, which means the two-sided limit doesn't exist, which means the function value can't equal the two-sided limit because the two-sided limit doesn't exist. The other type that we had here was a removable discontinuity. In this case, the limit does exist. Actually, let me just take this graph. Copy. Come down here. One more example here. Oh, we can't copy after we copy? Okay. Go back up here, do this again. Copy. Done here. Paste. Okay. So there's a graph. So like, let's say that this is a y value here. Let's say that this is a y value here of, let's just say 5, and let's say that this is an x value of 2. In this case, the limit, let's call it g as well, give it a name, g of x. The limit as x approaches 2 of g of x equals 5, right? Because you can trace that curve from the left and from the right, and you get to the same place, right? So you've got, from the right, you end up there. From the left, you end up there. I don't need to write out the two-sided limits. You can see that they're both 5, right? However, if you wanted to look at the function value, you have to have g of 5 as well. What is g of 5? Or sorry, g of 2. G of 2. Brain does not work today. G of 2. What is g of 2 according to the graph? Well, there's an empty circle there, right? There's an empty circle. Well, where's the solid dot at x equals 2? I didn't draw one. I didn't draw one, so this does not exist. Now again, these are not equal, right? They're supposed to be equal if it's continuous at 2. They're not equal, so not continuous at 2. Since limit as x approaches 2 of g of x is not equal to g of 2, because the right-hand side one does not exist there, then G is not. There's a lot of abbreviations for continuous. I usually just write CONT. G is not continuous at 2. All right, and there you go. We saw two things that were not continuous there. All right, now what they're going to do is, you're going to see a lot of different things in the homework. One thing you're going to see is you're going to see graphs like this. Like, let's see, I'll just draw one. This is straight off of your homework, except that I'm going to draw it by hand. All right. So we've got minus 1, minus 1. There's a dot right there. Then at minus 2, there is an empty circle right there. And then the graph does this. There's my graph. And this is a graph of, what do they say? F of x. So this is y equals f of x. Okay. Good enough. All right, and so what does the question say? It says, well, select the statements that are true, right? So basically, the only point that's interesting here is this one, right? X equals -1. So let's look at x equals -1, and let's see what we can say about it. Let's do the limit first. Limit as x approaches -1. Let's go from the right of f of x. And let's do the limit as x approaches -1 from the left of f of x. And let's look at f of 1. So there's 3 things we can look at here. So let's do it. So limit as x approaches 1 from the right. That would be tracing the curve on this side, right? So you trace the curve this way, and you should end up down at that point where that empty circle is. So where is that point? At a y value? That looks like a y value of -2. So that's -2. Then we can do the limit as x approaches -1 from the left. So you're on the other side. So you're over here somewhere. So you trace the curve from the left, like that. And what y value do you end up at? Answer, -2, again. All right, so far so good. Now then we have to work out f of, should be -1, f of -1. What is f of -1? Well, that's actually up here, right? Where that solid dot is. So f of -1 is -1, right? So, is this continuous at -1? The answer is no. And we should be able to say why. We should be able to say f is not continuous at x equals -1, and we should be able to say why. So our choices, this is a multiple choice question in the book, and so our choices are as follows. I'll just write them and we can decide. F of -1 is not defined. That's like choice A. Choice B, the limit as x approaches -1 of f of x does not exist. Or C, the limit as x approaches -1 of f of x does not equal f of -1. So we've already seen a couple of these options, right? So in option A, we would be saying that this value right here failed to exist. But that's not true, right? It exists. It's -1. Right? So that's not it, because it is defined. Option B. Option B says the limit does not exist. Well, the fact that these two-sided limits here, or the two one-sided limits gave us the same number, right? So since they gave us the same number, the two-sided limit does exist. It's -2, right? That's the answer we got twice. That's the answer for the limit. So this is wrong as well. So choice C says the limit and the function value just aren't equal. Yeah, that's the problem, right? One of them is -2, one answer is -2, one answer is -1, and those aren't the same number, and that's why. So this is it. That's what went wrong, right? The limit existed, the function value existed, but they were not equal. Okay? And that is a type of discontinuity. Now, another thing you're going to have to do is you're going to have to understand piecewise defined functions. And it's not as bad as you might think. I'm just going to steal a piecewise defined function here. Let's see here. All right. So let's look at a piecewise defined function. And this isn't really like its own category or anything, but this is what we want to work on. So piecewise defined function. All right. So this is going to look complicated. This is just an example. This is going to look more complicated than it is by far. All right, so let's say 2x squared minus 2x plus 1 if x is less than or equal to 6. Negative x squared minus x plus 2 if x is between -6 and 0. And then 2x squared minus 3x plus 2 if x is greater than 0. All right? And so, is this continuous or not? All right? Basically, on a piecewise defined function like this, the individual pieces are continuous. We haven't said it yet, but polynomials are always continuous everywhere. Right? So all polynomials are continuous. Right? They don't have holes or anything. So all polynomials are continuous. So the only places that this piecewise defined function might not be continuous at are the places where it switches from one function to the other function. This should have been -6, by the way. So it might not be continuous at -6, and it might not be continuous at 0, because those are the 2 points where it switches functions. Okay, but maybe this is not continuous at x equals 0 or -6, because that's where it jumps from one function to the other function. Now, I'm using the word jumps from one function to the other, but there doesn't have to be a jump there. One function to another. Right? Because just because a function switches at maybe 3, you could have a case where there is a jump like that, but you could also have a case where one function does that and the other one just might line up. And if it happens to line up, then even though it switches at 3, that's still a continuous function. Okay? Now, I think I don't want to leave these up, kind of in the way. But it might be continuous at -6. So If you want to investigate this thoroughly, here's what you would do. So let's look at x equals minus 6. So all you want to do is you want to evaluate the limit from the left, the limit from the right, and the function value. So you go limit as x approaches minus 6 from the left. Limit as x approaches minus 6 from the right. And then you also want f of minus 6. So these three things need to be worked out. Okay, now here's the thing. What do I put inside of that limit there? And that's what you have to think about. So if we're on the left-hand side here, so left of minus 6, you have to think about up here on the piecewise defined function, if you're to the left of negative 6, are you using the first piece, the second piece, or the third piece, right? Well, you're not using the third piece because the third piece is x greater than 0, right? And we're going to negative 6, so that's not right. Well, the second piece is between negative 6 and 0. That's actually to the right of negative 6 on the number line, right? Like the number line looks like this. So you've got basically these three pieces. The first piece is here, the second piece is here, and the third piece is here. So if you're to the left of negative 6, which piece are you in? You're here, right? You're here in piece 1. So you should be using this function. So you put that function in your limit, 2x squared minus 2x plus 1. Now how do you evaluate that limit? Well, it's just a polynomial, and we know you can just put the number in. So you put a negative 6 in. 2 negative 6 squared minus 2 negative 6 plus 1. Well, what's that? We got to work it out. So 6 squared is 36. 36 times 2 is 72. 72 plus 12 is 84. 85, is that 85? Okay, maybe. We'll fix it if we have to. The next one is limit as x approaches negative 6 from the right. Well, the right side of negative 6 is in here. So you'd be using the middle function. So that's negative x squared minus x plus 2. And then you have to put in a minus 6 again to see what you get. Minus 6 squared minus 6 plus 2. So you work that out. What are you going to get? Minus 6 squared is 36. But then our minus out front is minus 36. Minus 36 plus 6 is minus 30 plus 2, minus 28. I don't know. Something like that. All right. And then you need f of minus 6. Well, what about f of minus 6? Well, the first function is the one where it says x is less than or equal to minus 6. So we use the first function. So you put a negative 6 into the first function again, which we've already done once. Maybe we can check our answer. Okay, 236 plus 12 plus 1. All right, so yeah, 72 and 12 is 84. 84 and 1 is 85. 85. Okay. So look at the results there. We have an 85 from the left, negative 28 from the right, and the function value is 85. So is this function continuous at negative 6? No, it's not, right? Because these are not all the same. These would all have to be the same in order for it to be continuous, because you need the limit to exist. So these two have to be the same in order for the limit to exist. And then after that, you need that number to be equal to the function value, which is this number. So basically just all three of these just need to be equal for it to be continuous. They're not, and so f is not continuous at x equals minus 6. Okay? And then you can do the same thing for 0, which I'll do briefly here. Look at x equals 0. So we need a limit as x approaches 0 from the left. What function are we going to be using? So from the little picture here, looks like if we're to the left of 0, we're in the second function. So negative x squared minus x plus 2. So you put a 0 in there, you get 2. You need the limit as x approaches 0 from the right. All right. If you're to the right of 0, that's this case. So you're going to be in this function. So 2x squared minus 3x plus 2. 2x squared minus 3x plus 2 plus 2. So you put a 0 in there, you get 2. Then you need f of 0, which is, so equals 0 is in the second box, so you'll put a 0 in the second function, so you get 0 plus 0 plus 2 again, which is 2. So let's look at that. What did we get here? I got the same answer all three times, right? So the limit from the left equals the limit from the right equals the function value. So it is continuous. So f is continuous at x equals 0. So if they come up the same all three times, continuous at that point, right? The definition of continuity that I gave you said is f continuous at a? That's it. Okay. Let me just double check my video is still going. It is. All right. So that's more or less what you need to know about continuity. Now, another thing that you want to know, though, is intermediate value theorem, which try to do in 10 minutes here. We can do it. Intermediate value theorem. E. All right. What is the intermediate value theorem? So the intermediate value theorem has a complicated explanation, but then an easy idea to apply. All right. So let's see here. Intermediate value theorem. Here's what it says. It says if f is continuous on an interval a to b. All right. So only works for continuous functions. And yeah, actually that's it, right? If f is continuous on AB, then there is a C sorry, I have to erase this, said it wrong. Should have thought about the intermediate value theorem before I started writing the intermediate value theorem. So if f is continuous on AB and let's see, K, how we use K? No. I want to use the letters that the book uses. Sorry. They use a Z, really a Z. Okay. If f is continuous on AB and Z is between f of A and f of B, then there is a C in AB, that's an interval AB, such that f of c equals z. All right. So that's the intermediate value theorem. Now, like I said, that's initially a little bit hard to understand. But here's like an easy example of it in words that will make very easy sense to you. So, simple example. Let's take a function. F of x equals x squared minus 5. Okay. Now, let's put a 0 in this function. F of 0 is what? Well, you put it in the function. 0 squared minus 5, which is minus 5. Okay. Now let's put another number in there. Let's put 4 in there. F of 4 equals 4 squared minus 5, which is 16 minus 5, which is 11. Okay? Now, what's that mean on the graph? What that means on the graph is this. So you've got minus 5 down here, and 0 minus 5. It goes through that point. You've got another point, 4 comma 11. So let's just say like 1, 2, 3, 4. Let's go 5, 10, 10. So like 11 is just a little bit above there. So right about there. All right. Now, you've got those 2 points on the graph. And this is a continuous function. So if you're going to get from the point down here to the point up here, right, like that, then do you have to cross 0? I mean, I did cross 0, right? Like, how can you get, if you're trying to get from the point, oh no, that's not what I wanted. If you're trying to get from the point down here at the bottom to the point up here at the top, would you be able to do it without crossing the x-axis? Right? Get from 0, negative 5 to 4 comma 11 without crossing the x-axis? And the answer is no. Right? At least the answer is no if you don't lift your pen. If you lift your pen, you can go like this, and then jump, and then keep going, right? But if you don't do something weird like that, if all you're doing is connecting the dots, then you've got to cross through 0, right? And the intermediate value theorem is just the theorem that guarantees that. So the fact that one point is negative and one point is positive means that the function has to go through 0 there. So that's the easiest application, simplest application. If f of a is negative and f of b is positive, then f of x equals 0 somewhere. You don't know where, but somewhere in AB. Right? Because how do you get from a positive number to a negative number without going through 0? You don't. But that's only for continuous functions. For a continuous function f. All right? And that's really the main case that you are going to want to use the intermediate value theorem is for finding those zeros. But if this idea makes sense, that in order to go from a positive to a negative, you have to go through 0, then you really know everything you need to know about the intermediate value theorem, because you can apply it to other numbers as well. Example, let's say g of x. I'm going to use another polynomial, so I'm going to say like 2x squared plus x, right? So if I use the interval 0 to 5, okay, I'll say does g of x equal 10 somewhere in 0 to 5? Question mark. Now I don't need to solve that equation to answer this, right? Here's what you can do. You would just evaluate g of 5. I don't know why I'm starting with the 5 and not the 0, but I am. So do g of 5. You get 2, 5 squared plus 5. What is that? 5 squared is 25, times 2 is 50, 55. That's 55. Now g of 0. What's g of 0? 0 plus 5, which is 5, right? Now, 10 is between these, right? So if the function goes from 5 to 55, it must go through 10. And that's the intermediate value theorem. So you just say, since 10 is between g of 0, which was 5, and g of 5, no, was it? No, yeah, g of 5, which was 55, and g is continuous, you need a continuous function or this does not work. G of x equals 10 for some x in 0 to 5. And that's by the intermediate value theorem. All right? And that's the intermediate value theorem. But the primary application of it is what I said right here. Okay? If a continuous function is negative somewhere and positive somewhere, it must go through 0 somewhere, right? Because that's how you get from plus to minus or minus to plus, just like this picture, from a negative to a positive. Okay, got to go. I'm going to post this right now for you guys, and there'll be more videos coming.